Hello, welcome to another problem session. Today we're gonna we start on waves. So we're going to start on waves. A particular kind of wave that we're gonna study pretty much exclusively are called sinusoidal waves. So this is a problem with sinusoidal waves, and this is our first problem. I will be using a lot of problems from my website, physicsbootcamp.org. So what is this thing sinusoidal? So sinusoidal refers to a mathematical property. So sinusoidal is a math term. So it basically means the sines and cosines. Sometimes it's called harmonic also, because these are harmonic functions. And when we plot it in B, you'll see the shape, and which you're probably familiar with. Shape. Sometimes people just shape like that and say that's the wave, and maybe it's moving in that direction or moving in that direction. That's how you represent the wave. So it's like it's at some instant. So this is like a snapshot. At particular instant it looks like this. The next instant, if it's moving that way, then it will be keeping the shape, because and it will appear over there. So this is at some time t1 and some time t2. We'll see what our wave looks like here, but this is general idea. You may be familiar with this. Okay. So usually I'm going to use the letter psi. It's psi psi, or kind of psi, as it's sigh psi. So here is a say pressure wave, which is same as sound waves are pressure waves. Sound in air is like a pressure, is different location at a particular instant. So there is amplitude, and then there is a argument of a cosine we're writing. So the whole thing is a function of position and time, and so it's a one-dimensional. So the wave is this problem is along x-axis. So apparently there is some origin here, and so either is the wave is going this way or that way. We don't know yet, because when we analyze it, we'll know. It will turn out that if the x term and the t term, if they're both positive, then it's going to go that way. So our wave will be going that way, this one. If they're opposite sign, then it will be going to the right. And you will see why that's the case when we solve this problem. And then there is a units, etc. given here. So from this, I should be able to read off. So usually we should learn this thing with a cosine kx plus omega t minus pi over 4. So that's the way I can read off. This is the amplitude, this is the wave number, this is the angular frequency. So this is also called wave number. So and it's related with wavelength. It's the inverse of wavelength. K times the wavelength will be 2 pi. And this guy is related with frequency. Omega is maybe a time period. You can say time period is the inverse time period times 2 pi. And frequency is 1 over time period. So these are the basic relations that you should know. Okay. So reading off very easy. In A, amplitude is 20 Pascal. K is 1 over 15. If this is meter, then this will be 1 over meter. 1 over meter unit is so to get the wavelength, this would mean I just need to do this. So lambda is 2 pi over k, and k is 1 over 15, so this is 30 times pi meter. It's a pretty long wavelength. And omega is 5250 per second. That means from here I get a frequency, so omega 2 pi f. So f will be omega over 2 pi, and so 5250 over 2 pi, this will be per second, which is the same as hertz. Here 5250 over 2 pi cycles per second, which is hertz. Okay, how about B? Draw the wave at t equal to 0 and at a quarter of a period. So when we this is called phase constant. I didn't ask. Oh, I didn't even answer the speed yet. Yeah, the speed. Speed will be, this is where the position of the wave is changing with time, right? So if you look at just the top, how the, or any point of the wave and the corresponding points, this top compared with that top, in, so this is in different, how much time, how much distance this should go in that time. So that we can get 1 over 15x plus 5250t minus pi over 4 is some constant. So I'm just looking at a particular value in the cycle of the cosine. So this will mean just hit with dd, take a derivative of the whole thing with respect to time. So 1 over 15 dx dt plus 5250 times 1 minus 0 equal to 0. So dx dt, which is velocity, just turn it to be minus 5250 over 1 over 15 equals minus omega over k here. And minus, it means going to the left. This is what going to the left. And you have the 5250 times 15. It's probably not air, it's some in some medium. In air the speed will be not that high. So this will be this many meter per second. Okay. And I can just multiply it and get the speed. That's just not right. I think I was just constructing the problem and multiplying and dividing by 2 pi kind of messed up. That's why that number was wrong here. So this probably in some medium, like in a pressure wave in air goes about 350 meter per second, which is not that, right? In water, they go 1500 meter per second, etc. So more dense medium, uh, uh, and with elastic proper, it's related to the medium's density and elastic property. And in some medium, it can go this high, depending on the proper properties. Okay, but the number is probably not that important. You're trying to, if you want to learn this is more important. So I looked at a particular place in a cycle of the wave, and I say for the same cycle, which is the same cycle, the argument of the cosine related to the cycle position the cycle in the wave. So if this considered theta of xt, so that's a harmonic function. So you can see, you can think of in a cycle, like you can think angular position, and then I go one more whole thing and I come back to the same. So same position in the cycle, like top to top, bottom to bottom, maybe this point to that point, same position in the cycle. Then what is the phases will be related in the same manner, and this will tell me, if I take a derivative at a time, it will tell me what the velocity should be, and this is how I got the velocity. Okay, now to answer B, I'll just plot it. Okay, for B, how should we plot it? So at t equal to 0 is the function I'm plotting. So it's plotting a cosine kx plus omega t minus pi over 4. So at t equal to 0, so for t equal to 0, I'm plotting a cosine kx minus pi over 4. So if this you think of as a theta, so let's plot like this. So if I have a theta this way, so that corresponds to x will be 0, theta equal to 0. So because theta will be easy to plot, 2 pi 4 pi minus 2 pi, and you'll go from plus a to minus a. So let's draw the edge so that I have a nice limits within which this function will vary. Let's see, when theta is 0, cosine, the argument is minus pi over 4. This is the phase constant. So it's going to be, if theta is 0, so it's going to be, when theta is pi over 4 over here, when theta is pi over 4, that's where the peak is, right? When theta is pi over 4, that's the peak is. So it's going to be, peak will be again over here, again over here. So this is pi over 4, this is 2 pi over pi over 4, 4 pi over pi over 4. So this will be the peaks, and this is, so this is pi, this is pi over 2, this is pi over 4, this point, and this point 5 over 4. So this one is 2 pi, this is 3 pi, 2 pi, this 3 pi, 2 pi plus pi over 2, and this one will be over here. So this very close to, this is 4 pi plus pi over 4. Okay, let me plot this. is going to be 0 will be right here, and -1 will be down here. Uh, 0 will be a little bit to the right. This -1. So I really let me pause it. Okay, so another attempt at plotting it. So this is where I expect the maximum, and then maximum again over here. The minimum is down here. This is where the maximum is. This the maximum is. This where the 0 will be, and the 0 will be down here, and this is pi. If this distance is pi, I get minus pi here, and this is minus pi over 2. So this is where the 0 will be, minus pi over 2, minus pi, this pi over 4. This is where the 0 will be. This is pi over 2. This much is pi. This pi over 2. Pi over 4 is halfway. So this is 0 would be this where the 0 is. This where the 0 is. And so it's like this. So this is okay. So this is it. I can repeat this. And this is t equal to 0. So how do I plot this at a quarter period later? So look at this. At a quarter period later, this will be omega t, delta t. Delta t is t over 4, and this will become what? Omega t is 2 pi over 4 is pi over 2. So this is pi over 2. And now, so this will be, this will move over here. It moving to the left, so this top will move where the 0 was, because pi over 2. And so the next, let's see, it will be like over here, and the 0 will be down here. 0 will be down here, and where the 0 was is going to be the maximum. This will be moved. Yeah, so 0 will be down like this, and it will go through 0 here, and then it will go over there, and then it will go through here. So this is going to be, you repeat this for t equals to t over 4, t over 2, t over 4, I mean t over 4. So that's how we can plot this, and it shows that this wave is actually moving to the left. Used to be here, later it's over here, so it's moving to the left. We knew that already when we calculated dx over dt. Dx over dt was less than 0. Dx over dt was less than 0. Okay, that's for now. Later on, I'm going to talk about more properties of waves, like interference and diffraction. But this is good enough for lots of definitions. So I'll talk to you later. Bye.